Well, first of all, thank you very much for coming. So before I start my intros, I'll give you guys a little bit of introduction. So prior to DARPA, I'm a professor in chemical engineering at University of Utah. So I spent my research career in design materials, devices, and systems to optimize functionalities in biological systems, right? Especially in the brain-computer interface. And on top of that, I also taught biochemical engineering for about 10 years. So my interest here in DARPA spans also from materials all the way to a system. Right? Today I'll give you some overview, like what kind of topics I'm interested in. So one thing my team we're actually thinking about is actually in material synthesis and material growth. Right? Especially when I've been thinking about the space of increasing in complexity of inorganic materials. Right? As we think we're moving from material with a simple composition structure, like silicon, germanium, nitrides, right? And then we're moving toward to complex material with complex composition and the structures, right? For example, like complex oxides, intercalated superconductors, right? Then as we're moving toward this very complex material space, we're asking the question, so how can we precisely control atomic composition, structure, and uniformity in this new landscape of complex materials? So if we think about the conventional thin film technology, right, in the semiconductor industry or in our research labs, right, we rely on these physical vapor deposition techniques and the chemical vapor deposition techniques to grow our materials, right? And these techniques are totally fine to create material with a simple composition, right, and simple structures, okay? But I would argue fundamentally, these materials are unsuitable to make the material complex materials as we're moving forward in our complex material space. And it's time to really think about a different material growth technology now. So the reason actually is, if you think about it, as we increase the type of the items, right, within the material, and our dimension of our devices are continue to shrinking in the nanoscale, right? It's become increasingly very difficult for our conventional technique to be able to control the compositions and the structures, right, within the nanoscale, right? So if we have slight variabilities in atomic composition and the atomic placement, right, that will make a huge differences in like device performance and the device reliability, right? So that's why I think this is I think our conventional technique is kind of like painting, creating a very detailed painting, right? But with a fire hose. Right? It's impossible to enable this kind of nanoscale precision control in composition and structure. Okay? So that's why we ask the questions. So can we enable some additional controls and the pathways to enable precision composition and structure accuracy in complex inorganic materials? Okay. Then you would actually ask me, so why do you think that's possible? I think it's possible because biology offers us already a very good example of how we achieve complexity precision in material growth, right? So for example, we all know protein synthesis, right? In biology, in biosystems, protein synthesis, we can make proteins in precise control of composition and the structures, right? But in our biosystems, we don't do it by just flooding 20 different type of amino acid into a really large chamber, right? But how we do it in a biological system is actually we enable precision, spatial control, right? We control where the amino acid goes, right? And we also enable localized thermodynamic and kinetic control, right? In this molecular reactors, right? So then my question for you guys is, well, it'd be like, in our new material synthesis system, can we enable some of these controls that we have, similar to the biological system that move forward for our precision, complex material synthesis, right? So that's kind of one of the topics we're interested. Next, we're actually thinking about on a device level. So I've been working on the implantable devices field for a long time, right? So if you think about it, our devices, our microsystem devices is really constrained by the environment it operates in, right? And especially a lot of our devices is very vulnerable to the environmental, harsh chemical environment, right? For example, like acid, base, salt, and even like different kind of reactive species, right, in different environments. It's very vulnerable to that. In a sort of like conventional approach, we think about packaging, right? So we get a device, we know it's not gonna survive in that environment. Let's just package them, right? Find like corrosive existing packaging. But that oftentimes actually limits our device performance, right? The packaging typically can limit our device performance. So then actually my team actually very interested is actually thinking this differently, right? What about the environment is not a foe, right? It's not but it's actually our friends, right? When our design our devices, we think about the environment, thinking about the condition it operates in, right? Maybe the environment can actually enhance our device performance. Instead, we have to use crazy packaging to protect it, right? So that's sort of the framework we're operating under. So the example I would actually point out is kind of like in diamond synthesis, right? If we think about high temperature and the high pressure, we think they're not good, right? They're gonna break our material, right? They're gonna degrade our material. But it's actually not true in the case of diamond synthesis, right? We go from graphite and we go through really high temperature and pressure to actually create something that's very desired material property, right? So maybe it's time we're thinking our device design in the similar framework, right? How we utilize the environment to our benefit, okay? And lastly, I think Winnie earlier said we're probably not specifically interested in medical technology, right? Because we do have a biotechnologies office. And my colleagues in BTO, biotechnology office, is very interested in medical devices. But my colleagues in biotechnology office, they're very interested in taking existing systems, right, to enable new capabilities. So in this particular scenario, I think my colleagues in BTO actually convinced me that such a system doesn't exist. Maybe the microsystem people should take a look and think about it. Okay? So the example here is actually bleeding is the number one cause of casualty. Right? So on the battlefield, right? So typically we would want to stop the bleed within an hour to maximize survivability, right? So we call that the golden hour, okay? So for internal bleeding, it's extremely difficult to deal with, right, on the battlefield. It's because typically it requires a surgical procedure, okay? But obviously you can see that under a very constrained environment, there's no availability, right, for surgery, okay? So then that got me think, can we actually enable design microsystems, right, can actually stop internal bleeding without surgery, right? After talking to my colleagues at BTO, they don't think such thing exists, right? So the possible approaches could be, can we enable some of the non-invasive, focused energy approach in the microsystems, and coupled with, biological system can enable this, right? Ultimately, we'll be able to enable something that we can stop internal bleeding without any surgery, right? So yeah, so that's kind of the last topic I'm very interested in. And yeah, thank you very much for being here. Please feel free to talk to me afterward. There's a lot of smart people here. I'm open to all sorts of different ideas. Thank you.